What is voltage divider and how does it function and its application? What is a voltage divider? A voltage divider is a simple circuit consisting of two or more resistors connected in series, which divides the input voltage into smaller output voltages. It is a fundamental concept in electronics used to create a fraction of the voltage from a higher voltage source. How does it function? The voltage divider works based on Ohm's law and the series combination of resistors. When resistors are connected in series, the total resistance is the sum of individual resistances. The voltage drop across each resistor is proportional to its resistance. A voltage divider works based on the principle that the voltage drop across a resistor in a series circuit is proportional to its resistance. This relationship is governed by Ohm's law, which states equals times V equals I times R, where V is the voltage across the resistor, I is the current through the resistor, R is the resistance of the resistor. In a voltage divider, two or more resistors are connected in series, and the input voltage, V, is applied across the entire series combination of resistors. The total current, I, total, through the resistors is the same because they are in series. The key idea is that the input voltage is divided between the resistors based on their values. The larger the resistance, the greater the voltage drop across that resistor. Step-by-step functioning. Total resistance. When resistors are connected in series, the total resistance, R, total, is the sum of the individual resistances. For two resistors, 1, R, 1, and 2, R, 2, in series, equals 1 plus 2, R, total, equals R, 1 plus R, 2. Current calculation. The total current, I, total, in the circuit can be found using Ohm's law. Equals 1 plus 2 I total equals R total V and equals R 1 plus R 2 V and this current flows through both resistors because they are in series. Voltage drop across each resistor. The voltage drop across each resistor depends on its resistance. According to Ohm's law, the voltage drop across 1 R 1 1 V 1 and 2 R 2 2 V 2 can be calculated as 1 equals times 1 V 1 equals I total times R 1 2 equals times 2 V 2 equals I total times R 2. Output voltage. The output voltage V out is typically measured across one of the resistors, often 2 R 2. The voltage divider formula gives us equals 2 equals times 2 1 plus 2 V out equals V 2 equals V and times R 1 plus R 2 R 2. So, the output voltage is a fraction of the input voltage, determined by the ratio of the resistances 1 R 1 and 2 R 2. Example: consider a voltage divider with equals 10 V and equals 10 V 1 equals 2 omega R 1 equals 2 ohms 2 equals 3 omega R 2 equals 3 ohms. Calculate total resistance equals 2 omega plus 3 omega equals 5 omega R total equals 2 ohms plus 3 ohms equals 5 ohms. Calculate total current. Equals 10. 5 ohms equals 2 I. Total equals 5 ohms. 10 V equals 2A. Calculate voltage drop across. 2 R 2 equals 10 times 3 omega 5 omega equals 6 V out equals 10 V times 5 ohms 3 ohms equals 6 V. So, the output voltage across 2 R 2 would be 6 V. Summary of the functioning. The input voltage is applied to a series combination of resistors. The total current is determined by the total resistance of the series resistors. Each resistor drops a voltage in proportion to its resistance. The output voltage is taken from across one of the resistors, calculated using the resistor ratio. Applications of voltage divider. A voltage divider is a versatile and widely used circuit in various electronic applications. Below are some of the key applications where voltage dividers are commonly used. 1. Adjusting voltage levels. Purpose: to reduce the voltage to a desired level. Example: in power supplies, voltage dividers can be used to step down high voltages to lower levels that are required by different components or parts of a circuit. Application: if a 12V supply is needed for a microcontroller or sensor from a 24V supply, a voltage divider can be designed to output 12V. 2. Sensor interface. Purpose: to scale down or condition the output of sensors. Example: many sensors produce output voltages that need to be scaled down to a level that can be read by a microcontroller's analog to digital converter, ADC. Application: a temperature sensor, such as an NTC thermistor, might provide a voltage that varies with temperature. A voltage divider can be used to scale this voltage to a specific range for accurate reading by the ADC. 3. Biasing active components. Purpose: to provide proper biasing voltages for active devices, transistors, op-amps, etc. Example: in amplifier circuits, voltage dividers are used to provide the biasing voltages to set the operating point of transistors or to bias the non-inverting input of an operational amplifier. Application: a transistor amplifier circuit might use a voltage divider to set the base bias voltage, ensuring the transistor operates in the active region for amplification. 4. Signal conditioning. Purpose: to adjust the amplitude of signals for further processing. Example: voltage dividers can be used to reduce the amplitude of an input signal to a level that can be handled by other stages of a circuit, e.g., reducing an audio signal before sending it to an amplifier or ADC. Application: in audio systems, if a signal is too high for a specific input stage, e.g., an ADC or a low-power amplifier, a voltage divider can lower the signal to an acceptable level. 5. Reference voltages for comparators. Purpose: to create stable reference voltages. Example: voltage dividers are often used to generate reference voltages for comparators or for setting thresholds in voltage level detectors. Application: in a voltage comparator circuit, a voltage divider might be used to set a reference voltage that will be compared against an input voltage to trigger an output. 6. Creating bias for LED circuits. Purpose: to control the current or voltage for light-emitting diodes, LEDs. Example: LEDs require a specific forward voltage and current to operate correctly. A voltage divider can be used to limit the current passing through an LED to prevent damage. Application: in a basic LED circuit, a voltage divider could be used to ensure that the voltage across the LED is within its specified operating range. 7. Digital to analog conversion. Purpose: to generate a specific analog voltage from a digital signal. Example: a voltage divider can be used to convert a digital signal from a microcontroller or logic circuit to a specific analog voltage level. Application: when working with a microcontroller that outputs a digital voltage, e.g., 5V or 3.3V, a voltage divider can reduce it to intermediate voltage levels for analog control, such as controlling a motor speed or adjusting brightness in a light dimming circuit. 8. Voltage sensing and level detection. Purpose: to monitor and detect specific voltage levels within a circuit. Example: voltage dividers are used to reduce higher voltages so they can be safely fed into a microcontroller or ADC for monitoring. Application: in battery-powered systems, voltage dividers can be used to monitor battery voltage levels to determine the state of charge and decide when a recharge is needed. 9. Creating a tapped signal. Purpose: to extract a fraction of a signal from a larger input. Example: a voltage divider can be used to create a tapped output that provides a reduced voltage for specific purposes. Application: in audio systems, voltage dividers can extract a part of the audio signal to be sent to a secondary stage, such as a tone control or feedback loop. 10. Testing and calibration. Purpose: to create known voltage levels for testing or calibration. Example: voltage dividers can be used to generate specific test voltages for calibration of measurement instruments or to simulate different signal conditions in a lab environment. Application: in test equipment, such as oscilloscopes or multimeters, voltage dividers can be used to generate reference voltages for calibration purposes. Limitations in application. Loading effect: the presence of a load connected to the voltage divider can alter the output voltage if the load resistance is not significantly larger than the resistors in the divider. Power dissipation: high-power applications require careful selection of resistors to prevent excessive heat dissipation. Conclusion: voltage dividers are essential for adjusting voltage levels, conditioning signals, biasing components, and creating reference voltages in a wide variety of electronic circuits. Their simplicity and versatility make them a fundamental tool in both analog and digital electronics. Limitations of voltage dividers. While voltage dividers are simple and widely used, they do have several limitations that must be considered when designing and using them in circuits. 1. Loading effect. Problem: the output voltage of a voltage divider can be affected if the output is connected to a load with significant resistance. This happens because the load resistance becomes part of the circuit, changing the total resistance seen by the input voltage, and thus altering the voltage drop across the resistors in the divider. Impact: if the load resistance is not much larger than the resistors in the voltage divider, the output voltage will be lower than expected. Example: if a voltage divider is designed to output 5V, but the load connected to it has a resistance that is similar to one of the resistors in the divider, the voltage output will drop, leading to an inaccurate voltage. Solution: to minimize the loading effect, the resistance of the load should be much higher than the resistors in the voltage divider. Alternatively, a buffer, such as an operational amplifier, can be used to isolate the load from the voltage divider. 2. Power dissipation. Problem: voltage dividers can waste power, especially if high current is involved or the resistors used are of low resistance. The power dissipated in the resistors is proportional to the current and resistance. Equals 2 times P equals I, 2 times R. Impact: in applications where energy efficiency is important, such as battery-powered devices, using a voltage divider can cause unnecessary power loss. Example: if a high current is flowing through a voltage divider with low-value resistors, a significant amount of energy will be lost as heat, reducing the overall efficiency of the circuit. Solution: when energy efficiency is crucial, consider using other methods, such as voltage regulators or DC-DC converters, that are more efficient for voltage conversion. 3. Limited precision. Problem: the precision of the output voltage depends on the accuracy of the resistors used. Inaccurate or non-precision resistors can lead to errors in the output voltage. Impact: if high precision is required, the tolerance of the resistors, which can be 1%, 5%, or more, might introduce significant errors, leading to inaccurate voltage division. Example: a 5% tolerance resistor in a voltage divider might cause a variation in output voltage by several percent, which might not be acceptable in applications requiring accurate voltage levels. Solution: use precision resistors with low tolerance, e.g., 0.1% tolerance, to minimize errors in the output voltage. 4. Not ideal for high power or large voltage drops. Problem: voltage dividers are not suitable for high power applications where large amounts of current or voltage are involved. Impact: if large voltage drops are needed, e.g., from 12V to 1V, the resistors will need to have large resistance values, which could result in impractically high resistor values or excessive power dissipation. Example: a voltage divider that steps down from 12V to 1V might need resistors in the range of several kiloohms, which could result in an impractical setup if a large current is needed. Solution: in such cases, a more efficient solution like a voltage regulator or DC-DC converter is better suited, as they can handle high power with better efficiency. 5. Temperature sensitivity. Problem: resistors have temperature coefficients, meaning their resistance can change with temperature. This can affect the accuracy of the voltage divider, especially in environments with large temperature fluctuations. Impact: if the resistors are subject to varying temperatures, the output voltage may change as the resistance changes, which can lead to instability in the circuit. Example: in a temperature-sensitive application, such as in precision measurement systems, a voltage divider could introduce error if the resistor's values drift significantly with temperature. Solution: use resistors with low temperature coefficients and/or ensure that the voltage divider is placed in a thermally stable environment. 6. Limited output voltage range. Problem: the voltage divider can only provide a portion of the input voltage. If a wide range of output voltages is needed, a voltage divider might not be practical or sufficient. Impact: in applications requiring multiple, different voltage levels, a voltage divider may not be the most flexible solution. Example: a voltage divider might only provide a limited number of discrete output voltages, so for circuits requiring a wide range of voltages, a more complex power supply system might be necessary. Solution: use other voltage conversion techniques, such as using a voltage regulator or adjustable DC-DC converter. 7. Not suitable for high current applications. Problem: voltage dividers are generally not designed to handle high currents. When large currents are involved, the resistors must be able to dissipate significant amounts of heat. Impact: using voltage dividers in high current applications can lead to excessive heat generation and even resistor failure if not properly rated. Example: in power electronics where high currents are required, using a voltage divider could result in resistors overheating and potentially damaging the circuit. Solution: for high current applications, consider using other voltage regulation methods, such as voltage regulators, or designs based on active components like transistors or operational amplifiers. 8. Potential for poor regulation. Problem: the output voltage of a voltage divider may not remain constant if the input voltage fluctuates significantly, especially if the input voltage is not stable or regulated. Impact: voltage dividers are not ideal for cases where stable and regulated output voltages are required, especially when the input voltage varies. Example: in battery-operated devices where the battery voltage might drop as the battery drains, the output from the voltage divider would also change, leading to an unstable output. Solution: use a voltage regulator or other methods to ensure a stable output voltage regardless of input fluctuations. Conclusion: while voltage dividers are simple, cost-effective, and useful in many low-power and low-precision applications, they do have several limitations. These limitations include the loading effect, power dissipation, precision issues, temperature sensitivity, and challenges in high current or high power applications. For circuits where these limitations are problematic, alternative methods like voltage regulators, operational amplifiers, or DC-DC converters should be considered. In summary, the voltage divider is a simple yet powerful tool in electronics for voltage scaling and conditioning, but care must be taken regarding load resistance and power dissipation.